Welcome, welcome, welcome. So, I'm going to talk about some more sort of late stage magmatic or subvolcanic um, hydrothermal systems. So, they're mainly worried about epithermal as well as volcanic hosted massive sulfides or VMS type deposits. So, these deposits form quite close to the surface, so hence the volcanic, subvolcanic, and they're mainly related to volcanic sources because they provide the fluid, the heat source, and likely the source of the metals. So we're starting to look at tectonic environments a bit higher in the system in the cases of convergent margins than we were last time in terms of porphyry deposits. And we might also be considering seafloor sediments or seafloor systems, which we discussed earlier in the trimester. So in these cases, we have fluids that can be near neutral to highly acidic. They're fairly low to moderate temperatures, 100 to 350 degrees Celsius, varying salinities, and they can be derived from seawater, magmatic water, or meteoric water, or in essence, a mixing of these different types becomes important for metal deposition. So this is where we are for epithermal systems. In this case, we looked at the porphyry. We're back in our convergent margin. We're now looking more around the volcanic, subvolcanic environment associated with the movement of fluids off these underlying granites, as well as circulation of fluid in the from the surface. So these environments will be fairly evocative, and in terms of people being able to see what they're like, most of us have seen images of geothermal systems, and that's the kind of behaviour where we're getting these epithermal deposits. So intracratonic and divergent margins can be important for other plume-related mineralisation, which I'm not going to go through here. And rift and extension environments can be good for VMS deposits. So black smokers, which we discussed earlier in the trimester, and I'll touch again on later on. But here's just an idea of an intracratonic or divergent margin, which is distinct, but we might get VMS in these rifted areas where we can form essentially shallow crustal circulation, hydrothermal circulation cells. Okay, epithermal precious metal deposits. We are back here. Here's our volcano, very conical. We have our big magma chamber. We have our porphyry system here, so a high temperature, shallow crustal boiling process. In this case, it's a copper gold. We discussed yesterday. We can get fluids moving off this system, potentially interacting with meteoric fluids that circulate down and through. And this is our epithermal system. So we can classify them as two broad types, high sulfidation and low sulfidation. And this largely relates to the oxidation state, not specifically the sulfur. So we have two main types, and in this case, it's gold plus or minus silver, and these ones are gold and silver. And so they're slightly distinct in terms of their location, but it's largely related to the nature of the fluids within the system. So epithermal deposits form on the Earth due to percolation of groundwater, potentially with magmatic fluids, and they're divided into these two types, low sulfidation and high sulfidation. Low sulfidation are reduced environments. High sulfidation is oxidized and acidic environments. So they're going to produce distinct behavior for metal deportment and what complexes the metals and how they are mineralized, and also the nature of the alteration. So high sulfidation systems, here we are. This is a more detailed view of a caldera. So a big volcanic caldera, something like the Taupo volcanic zone, or maybe like Yellowstone. We have our heat source and our granite. We might have little plugs or rhyolitic material, and we have down-faulted ring faults, collapsed structures. And we have our sort of fluid. We might have hot springs where we have water circulating through, groundwater circulating through, being heated and steaming in these systems, and we might even get breccia pipes and things like this. So these superheated neutral solutions, 200 to 350 degrees, move up through the system, and it's unclear if they're coming from magmatic source or predominantly from the groundwater. But then we can, as they rise and cool, they can boil and deport out metals. So these are quite common for continental margin subduction zones, high sulfidation systems, and they're nearby to porphyry systems. So due to the high acid conditions, we get very strong clay alteration of the rock associated with acid leaching, as we discussed earlier in trimester. So it's predominantly argillic and advanced argillic alterations. We have oxidized environment with the deposition of sulfates like alunite and silica chalcedony. And these deposits generally contain only minor sulfide. So they're limited pyrite, and the gold and silver commodities are commonly found in electrum and silver in sulfur salts. So we can also get minerals like anagite, copper arsenic sulfide, which may contain some silver, but the mineral deposition is due to fluid mixing and decreasing temperatures and boiling. So the fluid is rising, it's cooling, might lead to a boiling and concentration, or it might interact with colder or different oxidized fluids. Gold occurs in other minerals like the sulfides or maybe free, and they're generally very fine grain sized. So here we are, here's our schematic again, slightly different. We're now looking at the right hand side. Here's our porphyry. Here's our high sulfidation system of copper and gold. We have acidic fluids, advanced argillic alteration, and this is usually proximal to the sort of volcanic setting. In contrast, our low sulfidation systems are further away. We have deep meteoric fluid, we have a neutralized area, so the fluids are not as acidic, and we have a reducing of the system, so potentially more related to magmatic fluids that are reduced. It leads to our low sulfidation system, and we get things like ageluria and sericite alteration as being more distinct versus our high sulfidation system. So in these settings, it's very common for us to get metal zonation in a vertical sense. This is related to the changing temperature of the fluid and its metal deposition. So gold complexes well, especially with sulfides or chlorine complexes. So it can be deposited very high in the system, above the boiling zone. As you go deeper, things like zinc, copper, lead, potentially silver, deport out of the fluid at higher temperatures. So they crystallized earlier, and we can get this zonation from gold to further down to more common base metals. Okay, low sulfidation epithermal, the fluids are dilute, higher in pH, so they're near neutral. The deposition of gold occurs due to periodic boiling events or mixing with other waters. So it can be related to the magmatic fluid or the meteoric fluid. Gold is usually free, so it's native gold, but it may also include as inclusions in sulfide minerals. And we term this gold and sulfide minerals as refractory, and depending which sulfides it is, it may be difficult to actually extract, which may make the deposits uneconomical. So here's just some nice examples of the styles of mineralization and veining in these epithermal deposits. So epithermal means shallow, remember. These are from the North Island of New Zealand, which is a classic setting for it. We get what we call crustiform banding with quartz and aduluria, where we have different episodes or periods of deposition as the fluid composition changes. And we might actually be able to establish a history here depending on the nature of the fluid deposition. Here's some other examples, potentially with some sulfides. You can see them weathering out. Beautiful, nice banding in these rocks. It's very spectacular features. Here's some from Queensland. And we have some quartz up to some bladed calcite, which is a texture indicative of boiling. And we can also get some more coliform or crustiform banding. So these are showing us the changing nature of the fluid associated with mixing, potentially boiling events. We've seen this one before. This is a strongly argillic altered volcanic from Drake. Some people have this tenement, so they know it well. Beautiful sphaerolite crystallization on the margins associated with quartz veins, which have a nice coliform texture. Okay, so these are the sort of modern settings that this is going on. Here's White Island, quite infamous volcano now since the tragedy a couple of years ago, where some people have died. But it's an active volcano. We see commonly steam. This is the hydrothermal activity, the fluid moving to the surface and degassing. We have these hydrothermal pools where we have, as you can see, nasty looking water, which probably has quite a acidic pH. I think there's an example from Yellowstone where someone went swimming and properly dissolved. So it's not the kind of nice place where we're steaming. We see a lot of sulfur precipitation here. The rocks are probably extremely altered in these settings. Here's another one from Taupo, beautiful geothermal system, bright precipitates sulfur here. You can see prominent alteration just occurring in the surrounding rock. Okay, so that's epithermal deposits. Quite important around the Pacific regions. And, you know, it's taking that volcanic system to slightly higher. Okay, I'm just going to probably move through this fairly quickly. We covered this very early on in semester, but another instance of a sort of subvolcanic system is a VMS. So these dominantly form in submarine environments. They're related to black smokers, and they form from the venting of hot metal-rich fluids onto the sea floor. And so we interact these hot fluids with cold seawater, and it precipitates metals as sulfides and forms chimneys. So they're predominantly base metal deposits, particularly copper, zinc, lead. And you get variation in the metal content, one to do with the fluids and two to do with the temperature of the smoker. So remember, black and white smokers have different temperatures. Here's just a nice example. Here's a submarine arm. You have these chimneys of sulfides forming in the black smoker. We can see some venting going on in the background here. So very spectacular undersea features. Here is the location of the major VMS deposits. So they're fairly diverse. There's quite a lot in the Paleozoic. And there's some debated big ones like Broken Hill and Mount Isa, if they're VMS or ZX. But they're fairly well dispersed, but they suggest that they're forming in either a rift environment or in the seafloor. Here's some in Australia. They've been exploited for a long time. So there's some quite prominent ones in Queensland, some in New South Wales as well. So here's this tectonic setting. We can have the classic, what we call cypress type, which is essentially forming in the mid-ocean ridge, and it might get abducted onto the surface. We can get other ones in these sort of accretionary areas, or back arcs, or rifting environments on the continental crust. So don't worry too much about these different styles. The main thing is to understand VMS deposits generally. So here's the broad anatomy. We would have the fluid moving through this chimney surface, venting out here and precipitating material in exhalative horizons. So we have a prominent hydrothermal halo, and we have a stockwork of sulfides, pyrite and chalcopyrite, in the area called the stringer zone. So then we have varying layers of different pyrites depending on the variability in the temperature. So, pyrite, chalcopyrite, then we might get into sphaerolite galena, and then galena, sphaerolite, barite, and then further away we get manganese oxides, which are then capped by sedimentary material on top. So these deposits, the circulation of the fluid is transformed by moving through the crust, and it becomes reduced and able to carry metals via chlorine complexes. And the sulfate in seawater is reduced to sulfide and carried in solutions, and the fluids may be heated by underlying magmas or varying geothermal gradients. So we can also get a metal zonation in these systems associated to the changing fluid flow up the chimney, as well as potential exhalative horizons depending on the temperature of the fluid. So in the pyrite stringer zone, we move from iron, copper, gold, and as we decrease temperature, we move towards zinc, and then into our later arsenic, antimony, mercury, etc. So we vary, but the main high-grade zone is up in the top part of the chimney where we get most of the zinc, lead, silver. So as the fluids are circulating, of course, we get alteration, and the common host rocks are volcanic. They can be felsic, they can be mafic, and they're strongly hydrothermally, dominantly by prophylitic alteration, so background sort of green schist facies metamorphism, but we can also get localized phyllic and argillic alteration closer to the chimney. So the alteration in the footwell zone of the deposit tends to be chloritic, and in the zones of the highest fluid interaction zone, or these feeder zones, we get the sericite quartz, so the higher temperature areas where we get more pervasive metasomatism. The sulfides will oxidize and be dispersed in seawater unless the deposit is quickly covered, so we need to cap it to keep the system reduced. And because the sulfides precipitate very rapidly, they're commonly laminated and very fine-grained. So here we are through an idolized VMS deposit. We have a string of sulfide, then we have the massive sulfide zone at the top here, where the minerals are precipitated out. We might get varying stockwork or brecciation down here. And you have this massive sulfide area, and further away you move into exhalative deposits. It can be hematite magnetite, so like banded iron style, or you get other exhalative manganese deposits, and you might get other sulfide-bearing epiclastic material deposited further from the vent. And here's just an example showing the typical banded morphology as this materials have been precipitated. So we go from we got a nice chalcopyrite rich material here into sphaerolite and galena, and then we're getting a bit of rhythmic banding, and we might also get pyrite and pyrrhotite in these systems. So you get massive, quite spectacular bands of sulfide minerals in these systems. So that's all there is for me today.